Okay, so welcome to section 6.2, which is inverse trigonometric functions. Inverse trigonometric functions. Metric functions. Okay, so let's recall. The graphs of sine and cosine. Okay, so x and y coordinate axes. So in this case, I'm going to use x as my argument, my angle, just to make things easier instead of theta and f of theta. So let's see, 1, 2, 1, 2. Let's just do 2 quadrants, so pi over 2, pi, negative pi over 2, and negative pi, with an amplitude of 1 and negative 1. Okay, so the graph of sine started at 0, went up to amplitude, back down to 0, and was symmetric with respect to the origin. That looks something like so. Not drawn very well, but you get the idea. Okay, so this is y equal to sine of x. Okay, so if that's true, note that this is definitely not one-to-one. So what I'd like to do is I'd like to restrict myself to that portion of the domain, which is one-to-one. So notice, if I look at the domain, that is values of the argument or angle, or x in this case, on which my function passes the horizontal line test, it looks like everything from down here at negative pi over 2 comma negative 1 to positive pi over 2 comma positive 1 is one-to-one, just this portion here. Make it thicker so we see which portion I'm looking at. So I can take the inverse of that portion because only that portion, or others like it, are one-to-one. So therefore, x and y coordinate axes, if I want to take the inverse of that portion, basically I'm swapping x and y, or reflecting that portion of the graph about the line y equals x. So it's now my horizontal axis that will have negative 1 and 1, and it's my vertical axis that will have pi over 2 and negative pi over 2, because I'm swapping each instance of x and y. So instead of the point here at negative pi over 2 comma negative 1, I'm now at negative 1 comma negative pi over 2. I still have the point 0, 0, swapping x and y doesn't change anything there. And finally, the point at pi over 2 comma 1 will be at 1 comma pi over 2. I also know that it's going to be reflected about the main diagonal. So instead of being concave up to the left, it'll be concave down because it's a reflection. And then to the right of 0, instead of being concave down, it should be concave up, because remember, I'm reflecting it about the main diagonal. So this is the whole graph of y is equal to sine inverse of x, and I'll get to the notation in a moment. Okay, so let's do the same analysis for cosine. Let me give myself a little bit room here. Okay, so let's plot cosine. So we have, once again, I'm using x and y instead of theta and f of theta, but hopefully that makes sense by now. So x and y, let's do 1, 2 quadrants forward and 1, 2 quadrants backwards, so pi over 2, pi, negative pi over 2, and negative pi, amplitude of 1 and negative 1. Now cosine started at amplitude. So cosine starts at amplitude and is symmetric, meaning a mirror image on either side of the y-axis. looks something like so. Ugh. Trying to do this. Okay, there we go. So clearly this is also not a one-to-one function. However, if I restrict myself to that portion of the domain that is between x equals to 0 and x equals to pi, I notice that this region here, which of course was hard for me to draw, but hopefully I can do it. This region here is one-to-one, meaning just this specific region, and others like it pass the horizontal line test. Okay, so this is the plot of y equals cosine of x. So let's go ahead and plot the inverse function. So x and y coordinate axes. I'm going to make my y-axis a bit bigger. You'll see why in a moment. So x and y. So we have pi over 2 and pi now on my vertical axis, and +1 and -1 on my horizontal axis. Okay, so this point here at 0, 1 is now the point 1, 0. This point here at pi over 2, 0 is now the point 0, pi over 2, swapping x and y. And this point here at pi, -1 is now at -1, pi. Okay, so in order to reflect this, I note that this will be concave up till I get to pi over 2. Remember, it's going to look like a reflection across the main diagonal, and then concave down to get to 1. Something like so. Okay, so this is the graph of y is equal to cosine inverse of x on the restricted domain. And let me actually note that that domain was just from 0 to pi. Okay, so actually, yeah, let me note that actually. So the domain here is going to be from -pi over 2 to pi over 2. That's 1-to-1, right? Okay. What else do I want to do? The domain for cosine. Okay, so the domain for cosine. Did I put it beneath? Yeah, I did. So the domain for cosine is going to be from 0 to pi. The restricted domain, that is. And that's where it'll be 1-to-1. Okay. And I want you to notice that the range of the inverse function is the same as the domain. It's from -pi over 2 to pi over 2. So the range of the inverse function is the same as the restricted domain here. It's from 0 to 1. Sorry, 0 to pi. What am I saying? Okay. So definition. Okay, so let's let y be equal to sine of x for x between what interval? Well, the restricted domain was from -pi over 2 to pi over 2, right? For sine. Ugh. So from -pi over 2 to pi over 2. Then now do I want to say, I'll just write then inverse sine of x. Let me write it that way. Then inverse sine of x, that's what we're defining. Sine of x denoted by denoted by y is equal to sine, and notice the inverse comes before the x. Alternately, we can write it as arc, A-R-C sine. Remember, the arc is what is on the curve, but this is archaic, no pun intended. So has domain from -1 to 1, the inverse sine that is, and range. Well, I know the range is the same as a restricted domain, -π/2 to π/2. But let's go back up and make sure that the domain of the inverse sine is indeed from -1 to 1. -1 to 1, check mark. Okay, good, we got it. Okay, so let's note the annotation. So note that if we have y equal to sine inverse of x, that is equivalent. So if and only if, that's what this symbol means. So it's equivalent to x is equal to sine of y. So that is, if I swap each instance of x and y, technically I've found the, quote, inverse function. Okay, so let's do another definition, this time for the cosine. So definition. So let's let y be equal to cosine of x for, what was the restricted domain for cosine? Well, that was from 0 to pi. So for x between 0 and pi, then inverse cosine of x, inverse cosine of x, that's what we're defining. Inverse cosine of x, denoted by y is equal to, and once again, cosine and then inverse and then x. Alternately, we can write it as arc, A-R-C, cosine of x, has domain from -1 to 1, and we'll check that out in a moment. And of course, it's range, and range, which is the domain, the restricted domain, so that's from 0 to pi. So let's see if the inverse function for cosine, yes, the domain was from -1 to 1, and the range was indeed from 0 to pi, so that works. Okay, and once again, let's note that if I write y is equal to cosine inverse of x, that is equivalent, so if and only if, x is equal to cosine of y. That is, I swap x and y to find the inverse function. Okay, so for example, so evaluate the following. Okay, so number 1, let's evaluate y is equal to cosine inverse of the square root of 3 over 2. Okay, so what I'm going to do is, what color should I use? Guess I'll use purple. Y equal to cosine inverse of the square root of 3 over 2 is equivalent, so if and only if, the square root of 3 over 2 is equal to cosine of y. So now I have to ask myself, okay, at what angle, quote, y, remember these are angles now, at what angle is cosine equal to root 3 over 2? And that angle, y, is 30 degrees, or pi over 6 in the first quadrant. Agreed? And notice that pi over 6 is at in the domain, the allowable domain for cosine, which was cosine inverse, which was from 0 to pi? Yes, it was, so I'm allowed to have that, and that is indeed in the interval from 0 to pi, so I'm okay. We'll come back to that in a moment. Okay, let's do another one. So number 2, let's say we have that y is equal to sine inverse of 1/2. Sorry, let's do negative 1/2. Kick it up a notch. Okay. So we have that y is equal to sine inverse of negative 1/2. Kitty, what are you doing? Which is equivalent to swapping the argument, meaning I can write negative 1/2 is equal to regular sine of y. So now I have to ask myself, okay, at what angle, y in this case, is the value for sine negative 1/2? You might say, okay, so the y-coordinate is negative in quadrants 3 and 4, so sine is negative in quadrants 3 and 4. But remember, the allowable domain for sine inverse is between negative pi over 2, that is the 4th quadrant, and positive pi over 2. So sine is 1/2 at a reference angle of pi over 6, so this is negative pi over 6, which is forced to be between negative pi over 2 in the 4th quadrant and pi over 2, the 1st quadrant. Okay, so number 3. Let's say we have y is cosine inverse of negative 1. Let's do this in green. So we have y is cosine inverse of negative 1. So that's equivalent to, if and only if, negative 1 is regular cosine of y. Okay, so I have to ask myself, at what angle is cosine negative 1? Remember, cosine, we're only allowed to have the inverse of cosine between 0 and pi. Well, thank goodness I can have it at pi, because y equal to pi, cosine of pi is negative 1, and that is indeed between 0 and pi. Okay, one more for good measure. Number 4. Okay, so let's say we have y is equal to sine inverse of 0. Okay, so y equal to sine inverse of 0 is equivalent to, without the inverse, 0 is equal to regular sine of y. We always want to get rid of the inverse. That's our first step. So at what angle, where is sine invertible? Sine is invertible between negative pi over 2 and positive pi over 2. That is in quadrants 1 and 4. So where is sine 0? The y-coordinate is 0 when the angle is 0, and that is indeed between negative pi over 2 and positive pi over 2, so we're okay with that.